Hello everyone. In this lecture, we will learn how to initialize big data sets to enhance the accuracies of the neural networks. And this lecture is based on the lecture from YouTube, which are 3.1, 3.2, 3.3. The lecturer appreciates these three wonderful lectures that's taken from YouTube. Again, the weights should be initialized to enhance training accuracies. Initialization can have a significant impact on achieving a good training of deep neural networks. The nodal values of the previous node are assumed to be equal to 1, whereas weights on different neural links are assumed to be from W1 to Wn. Let's also assume weights are randomly generated, having a normal distribution with a zero mean and standard deviation of 1. The neural outputs here, Z, which represents a neural values of next layer, are obtained by multiplying neural inputs here in the circle of previous layer of all previous nodes of previous layer by the respective weights. Okay. Nodal outputs at a layer Z are obtained by multiplying nodal inputs of all previous nodes of the previous layer by the respective weights. As you see here, all the nodal values of previous layers are multiplied to the weights on different neural links to get a Z neural values of next layer. This one will be the tentative neural values if that's not applied with the activation function yet. The variance of the neural outputs will be sum of the variance of all independent weights you see here connected to at node Z when all previous nodal inputs of the previous layer are assumed as equal to 1. To the definition of variations, you see these formulas, and they are from each individual weights. Here, if the weights are applied to the nodal point of the previous layer, which are equal to 1. And standard deviation is calculated accordingly by this formula. Again, the weights are generated from the mean value of 0 and standard deviation of 1 with normal distributions when they are assigned randomly. So this formula will show you how to calculate variations. This is very important. So the your variation calculations of Z is just calculated by summing the variance of the independent weights connected to Z, which is W1, W2, W3 to Wn. You see here as well, this is a Z value, and you need to calculate each variance of each weight to come up with the variance at Z when the values of previous nodes are equal to 1. Because the previous nodes are equal to 1, you will calculate your variance at Z by summing all the variance of the independent weights connected to Z node of the next layer. And a number of nodes, neurons in the previous layer increases. If these are increases, see over there, these nodes are increases. See over there, 1, 2, all the way, and if we increase node from n to n plus 1, n plus 2, and so on and so forth, the variance of the nodal outputs at layer Z of the next layer will also increase even. Okay, the independent weight that has been assigned randomly, and the variance increases, therefore standard deviations here increases. When a number of nodes increases, as you see here, the variance and the standard deviations of the nodal points or nodal outputs or nodal circles for extended nodes, neurons, at each layer Z will be larger than those based on the weights which is not extended. The variance of node Z is determined by summing all the variance of all independent extended weights connected to node Z, and hence the nodal distribution of the nodal values at each layer Z becomes broader than the normal distributions with a standard deviation of 1 of the weights or links when they are not extended. And what's going to happen if we increase variance here by increasing a number of nodes right there? If we increase this, what's going to happen? The larger standard deviation of the nodal values at layer Z significantly spreads the normal distributions of the nodal point or nodal values at Z. See here, we're going to have a significant spread from the original statistics here when you add number of node, which resulted in the increased variation and increased standard deviations. And okay, so what's going to happen is that these spreadings of the normal distributions results in a significantly positive larger or negatively smaller nodal values of each layer. So if you see over there, you're gonna spread your shape here from normal distributions. So when you increase your number of nodes, it also increases a variance and standard deviation of nodal values at Z here. And this widely spread weights cause widely spread variance and standard deviation again, but that will hinder back propagations. So why is that? We're gonna take a look at the activation functions for that. As you see here, for very large x-axis here, and for very large absolute value of negative regions right there, our slope or gradient of the activation function becomes 0 or almost the zeros right there. The gradient vanishes because you are into a non-linear regions for very big positive x value or very small negative x value. You consider very small negative x-axis or absolute value for both positive and negative. Very big absolute values for both positive and negative values here. Okay, very big absolute values for positive and negative values here. Your gradients vanishes right there, and this will hinder your back propagation. That will be explained right now. Again, this back propagation algorithm will be explained very soon. When you go backwards to revise your weights from here to here. This process is called the back-propagation. When you go back-propagation, you try to find out error, the rate of error respect to weights. This is very important right there. So in order for us to reduce errors accordingly based on this ratio. Okay, so the error is calculated based on feed-forward network. And you calculate error, and you evaluate the error respect to the rate of error respect to weights, and this is very extremely difficult to calculate at once because you have plenty of the neurons in between the output and input layer. So what's gonna happen is to use a chain rule to drive your equation in terms of each terms, as you see over here. For example, the round error and the round weight is what you're gonna aiming for, so that you insert the neurons inside right there using a chain rule. This is a cancer, and this is cancer all the way. This is cancer. So you're gonna end up with this eventually, but this one is what you need. So you have all these terms in between, and these terms are related with the gradient of the neural values in between. For example, this is a gradient of neural values in circle. Circle means the neural values. I'm sure that these neural values are fed into the activation function. When you do this, the gradient of the value vanishes. Gradient vanishes. The until vanishes. So when gradient vanishes, in other words, you're having a very small number here, then you multiply many of these for one epoch, and you have to do this for maybe 20,000 epoch and 30,000 epoch, as I explained, for particular reinforced concrete design that I have experienced. And of course, then all this back propagation cannot do anything when all the terms in middle vanishes. That's why we say that the back propagation is hindered when you have a very big x-axis, which is right there, very big neural values on large absolute positive regions and large absolute negative regions. And you go this spread neural values for very large values here, very big values here, very big values in negative region here. It's going to eventually come up with a vanishing of gradient, because at here at very large positive regions, and also very absolutely large for negative regions, whatever, you're gonna have a vanishing gradient here. You're gonna have vanishing gradient. This is what happens, and this is what your back propagation bad, which means that your trainings to devise your weights and bias are very hindered. So we need to do something to decrease this spread, widely spread distribution of the neural value back to the original, if you can, like this. So the weights to shrink, variance and standard deviation is going to make your back propagation keep going, keep moving towards the revision of your weights and biases. That's what we are intended to do. And actually they are done by excellent researches by he and maybe Xavier's and Gareth and those people find a way to shrink these weights from widely spread neural values. So I'll write that again. This is person who develops how to generalize, and Xavier, this is one of them, very important people in initializations of big data sets. And we have a bunch of more people, and I'll try to explain that later who they are. The poor distributions of the weights lead to vanishing or exploding gradient issues when the weighted sum takes on variance that is relatively large. So as you can see here, if your values here, gradients is very big, very large, then all these multiplications becomes exponentially increases, exploding your back propagation process again. So we call that exploding. So exploding occurs when your gradient is large, which has to be multiplied many times throughout the old epochs, so that the vanishing, when you vanishes the gradients, or exploding when you get a large gradients, vanishings and explodings are both should be removed from the back propagation process to get a good training results. We need a narrow distributions of the weights are required to prevent the vanishing and exploding gradient issues during training. Here we need to narrow the distributions. Okay, here adjusting weight distributions called weight initialization. That's called a weight initialization. Okay, therefore the narrow distributions of the weights are required to prevent the vanishing and exploding gradient issues during training. Adjusting weight distribution called weight initialization is performed such that the weights are small and exhibit good variance. Again, these are very well explained in the references that I introduced, 3.1, 3.2, 3.3 of the new 2 lectures. You are free to refer to those references, excellent references. The variance of nodes in each output layer, Z, is determined by the variance of the weight connected to each node from the previous layer, as I explained already. Therefore, the variance of the weight should be reduced further to reduce the variance of the weighted sum at the neural outputs, Z of next layer. Okay. Of course, the mean of the weight should be maintained at 0. The issue is then how we can do this. How we can, let me just clear some part here. How we can reduce the distributions of the neural values of next layer to get a back propagations keep going. Here we have some formulas. Here if we multiply some values which is less than 1 here, we can reduce the weights. Okay, we can reduce the weight by multiplying some small numbers here, which is probably less than 1, then we can reduce the weight. If you reduce weight, then we will reduce, you see here, we reduce weight here, then we will reduce all this variance here. If you reduce W here, which is weight, then you're going to have a reduced variation, of course, as you see over there. Well, the reduced weights are used to calculate variance, which is also reduced as you see over here. And this is the way we should do to get the backpropagation going. And what do we do for that achievements? And there are people, as I say, including he and Xavier, propose a very interesting and excellent method to achieve this goal. And from now on, we're going to take a look at brief summaries of their achievements